Welcome to a deep dive into the invisible foundation of large language models, tokenization. It's the critical first step that bridges the gap between human language and machine logic. Computers don't understand words, they understand numbers. Tokenization is the process of breaking down raw text into discrete units that a neural network can actually process. Historically, researchers experimented with different levels of granularity. Character-level tokenization is simple but results in extremely long sequences, making it hard for models to learn global relationships. On the other hand, word-level tokenization creates a massive vocabulary, leading to the dreaded out-of-vocabulary problem where the model fails to recognize rare words or new variations. The solution? Sub-word tokenization. By breaking words into meaningful pieces, models can handle rare words while keeping the vocabulary size manageable. One of the most popular algorithms is byte pair encoding, or BPE. It starts with individual characters and iteratively merges the most frequent adjacent pairs. While BPE is common in models like GPT, others use WordPiece or SentencePiece, which use probabilistic models to determine the most optimal merges for a given dataset. Every model has a fixed vocabulary, a list of all the tokens it was trained on. Each token is mapped to a unique numerical ID, turning language into a mathematical sequence. Beyond standard text, models use special tokens to indicate the start of a sequence, separate different parts of an input, or pad sequences to a uniform length. This mapping directly impacts the model's context window. Since every model has a maximum sequence length, efficient tokenization allows it to remember more of the conversation. An efficient tokenizer balances vocabulary size and sequence length. Too many tokens make the model slow, too few make it lose semantic nuance. Tokenization also plays a huge role in multilingual models. Different languages have varying token efficiencies, which can affect the performance of the model across different cultures. Before tokenization even begins, raw text must be pre-processed. Normalizing whitespace, handling casing, and removing noise are all essential steps for a consistent output. During training, the choice of tokenizer is final. Changing the vocabulary later would require retraining the entire model from scratch, making it one of the most critical early design decisions. In some cases, tokenization can even impact security. Adversarial tokens can sometimes bypass safety filters if they aren't properly handled by the tokenizer and the model. Once tokens are converted to IDs, they are mapped into a high-dimensional space through embeddings, but that's a topic for our next deep dive. To summarize, we clean the text, break it into subwords using algorithms like BPE, and map those pieces to numerical IDs within a fixed vocabulary. Researchers are already looking at token-free models that process raw bytes directly, potentially eliminating the need for this complex intermediate step. But for now, tokenization remains the silent gatekeeper of the AI revolution, determining how effectively we can communicate with these massive neural networks. Whether you're building local models or using massive APIs, understanding the math behind the words is key to mastering LLM optimization. The next time you prompt an AI, remember the trillions of tokens being processed in the blink of an eye to bring that response to life. If you found this deep dive helpful, hit that follow button for more in-depth technical breakdowns. Let me know in the comments what you want to see next.